Well, we have a bottle of milk of magnesia right here. And this is magnesium hydroxide. So, so what we're going to do is we're going to get the pH value of the milk of magnesia. And from that pH value, let's see if we can calculate a KSP value for magnesium hydroxide. So this is an antacid, which we've talked about before. And notice I've got a pH meter right here. And there's the pH, that's water. So water, the tap water in this room's a little bit basic, as you can see, because they buffer it slightly to help protect the old-fashioned lead pipes that run throughout various buildings in this wonderful historic town of Alton, Illinois. Anyway, there we go. Let's check the pH of the magnesium hydroxide, which is here. And we'll give it a little bit of time to catch up. That out of the way. Give it a moment. All right. So here's what I want you to do. Write out magnesium hydroxide, solid. Show the equilibrium with the aqueous, slightly soluble ions. Write the KSP expression. Then let's go with a value of 10.0 for the pH value. So 10.0. And with that number, determine the KSP value. Give it a shot. All right, so here we are with magnesium hydroxide. We've got the solid magnesium hydroxide. We've got the equilibrium expression here. Notice we've got the pH. Let's call the pH, make the math nice and easy, pH of 10. First thing we need to do, let's write the KSP expression. And that's going to be quick and easy. Don't forget the charges here. And there's our hydroxide, and we'll square that. So what we're looking for here, this is what we're looking for. All right? Well, if we were going to do an ice problem, we would have ICE, and we've got our straight line here through this solid. We'll start off with 0 and 0. Oopsie daisies, make sure we get the stoichiometric coefficients there. And notice this is going to increase by a factor of s. This is going to increase by a factor of 2s. And at equilibrium here, we have s and 2s. So let's put s and 2s into our KSP expression here. Show your work in a systematic way. You need to show your work where a 6th grader can follow it. Show your work. Don't scatter it all over the place. You know who you are. Anyway, here we go. That, of course, equals 4s cubed equals KSP. So what do we know here? Let's see. This is, let me start over again. What don't we know? We don't know the KSP. So we do know that the pH value is given. And from the pH value, I think we could determine the 2s quantity. Of course, we got to convert the pH to the POH, and then the POH into the hydroxide ion concentration. So that's a really good place to start here. So again, looks like the pH is 10. So what that means is the hydrogen ion concentration, H positive ion concentration, is 1.00 times 10 to the negative 10th, pretty low. And since, let's review. Since we have the H positive ion concentration, we can times that by the hydroxide ion concentration, and that number is going to be a constant value. And if you recall, that equals the Kw. This is an equilibrium number, so that's going to be constant at that temperature. We know this quantity here at 1 times 10 to the negative 10th, so this quantity is 1 times 10 to the negative 4th. So here's our hydroxide ion concentration. We can write that here. 1.00 times 10 to the negative 4th. Well, let's do this here. That value, that 1 times 10, 1.00 times 10 to the negative 4th, that value equals 2s, right? Because we got to account for the stoichiometry. So, what does s equal? Easy enough, 1.0 times 10 to the negative 4th divided by 2. That's going to be our s value. Then we can take our molar solubility, but of course remember that is this quantity here. I like to convert concentrations to s and then just simply follow the arrow here and then just simply plug it into that value, and then we'll get the KSP. Go ahead and calculate that value. The KSP value, that is. In the number here, so we plugged in our S value. Again, I like to convert solubilities to S and then throw them into the into this handy-dandy, easy-peasy formula here. So I have my S value. There's my S value, and don't forget to cube it, times it by 4. There's my KSP value. Hold up. Let's go negative 13. So 5.0 times 10 to the negative 13. Well, how does this compare to the actual value? This is an experimental value, so to speak. So notice here's, all right, so how does our experimentally determined KSP value, how does that match up with the known KSP value? And let's do a little experimental error. So let's take the experimental value here. Let's subtract it from the actual value. Let's divide by the actual value, take it by 100%. Notice, we know the experimental value is this, so it's 5.0 times 10 to the negative 13th. The actual value I looked up, and that is 1.2 times 10 to the negative 11th. And then we'll divide by 1.2 times 10 to the negative 11th. And let's figure out the percent error. So go ahead and do that now, quickly. So what do we got here? What do we have here? It looks like our percent error is about negative 96%. So 96%. Don't let the negative throw you. That just means that this value was less than that. So we have quite a bit of experimental error. I don't think we did anything wrong. Is the pH meter wrong? There's no reason to believe that at all. So how do we account for this? Here's the milk of magnesia. So there's certainly magnesium hydroxide, and it's 1,200 milligrams per 15 milliliters. So there's the concentration. But as I look at the ingredients, not only do we have the magnesium hydroxide, so we have light mineral oil, we have saccharin sodium, we have peppermint oil. So maybe being this far off isn't that surprising. We did not have pure magnesium hydroxide here. So this is all important. It's all a really good, the concepts are really important in terms of what you're going to be asked to perform when we see each other again in terms of the final exam and on a test. All right, that's the end of this little segment. I do want to maybe do one more demonstration, and I'm beginning to think that I shouldn't have drank any of this. This is a laxative, so I gotta go. All right, let's say we have a saturated solution of the barium fluoride. And now what I want you to do is make a prediction here, justify your answer. We've got this saturated solution. What would the effect be on solubility now? The effect on the solubility, and when I'm talking about solubility, we're talking about the amount of ionization that's going on here. What would the effect of solubility have if we added an acid to a saturated solution of barium fluoride? Everybody, make sure, make a prediction. Increase, decrease, stay the same. Justify your answer. Go ahead and do that. All right, so here's my solid barium fluoride down here at the bottom. We have partial ionization going on here. What's the effect of adding an acid? Well, what we're asking here is, do any of these species here, these ionization species, do they react with the acid? So we add H positive here, so we'll do H positive in red here. So would H positive react with this? Of course not. It's not going to react with the barium double positive. Would it react with F minus? So really what we need to realize is F minus a relatively strong conjugate base? Because if it is, it's going to react with it. Is F minus a relatively strong conjugate base, or is this a neutral species? Not going to be an acidic species. Well, if you recall, if we have HF, HF is a weak acid. It's going to ionize partially here to H positive plus F minus. Of course, this would be a Ka situation. And just to review, we could put our Ka expression here where these products are going to go here and HF aqueous is going to go here. These are all aqueous, of course. Anyway, weak acids have a relatively strong conjugate base. So this is this has basic properties, basic in blue. Again, it's basic relative to water. So would this, I can change the color now, this is F minus is has basic properties. So now notice this would in fact react with F minus. So if H positive reacts with F minus, that would decrease this concentration. And notice here, again, it's going to shift the equilibrium in this direction, and solubility is going to increase. So this solid down here at the bottom, which is the barium fluoride solid, is going to start becoming more and more soluble the more acid you add. So, kind of cool. Notice here, this is magnesium hydroxide. What would be the effect of adding a base to this? Go ahead and answer that. Is solubility going to increase? Is solubility going to decrease? Or is solubility going to remain unchanged? Give that a shot. I like that blue color there for that base. Of course, while you're doing that, you could have Kb value here. Kb expression, just reminding you. All right, so here's my saturated solution. Here's my solid magnesium hydroxide. Notice here's the equilibrium written out in a more traditional way. Notice, if we're going to add a base, what's that going to do to the solubility? Well, let's see here. So let's add a base, sodium hydroxide, let's say. Sodium hydroxide is 100% soluble. The Na positive is not going to influence any of this. That's going to be neutral. What about the OH? By adding the sodium hydroxide, this is going to go up now. Notice, if this goes up, the equilibrium is going to shift again. Classic example of Le Chatelier's principle. We've had a lot of those. I realize that. Lots. Your final exam. It's going to be all over the place. And by the way, we're preparing for the AP test, but we are also preparing for my final exam. This is really important, really important. So notice this goes up. This is a good example of the common ion effect. We've added sodium hydroxide from an outside source. The hydroxide ion goes up. The equilibrium is going to shift in this direction, reducing the solubility of this substance. Okay? Good example of the common ion effect. Whenever we add a common ion from an outside source, we're going to see this happen. Let me grab this. Let's say, let's start over here. We're considering the same substance, the magnesium hydroxide. What if we're going to add, let's go with magnesium chloride. So let's add magnesium chloride. So there's our magnesium chloride salt. We're going to add that. Into the container here. Notice it's going to ionize, and it's going to release magnesium double positive. So this is added, common ion. This is going to go up. Again, this magnesium ion is going to result in a decrease in solubility because we're going to shift in this direction, and we're going to have less MgO2 ionizing here. Now, what's the effect of the Cl minus? So notice we also have 2 Cl minus aqueous in terms of which came from this solid salt. Is that Cl minus going to react with this? Of course not. Cl minus is neutral in its basic properties. It's neutral, remember? Cl minus. That's the conjugate base of hydrochloric acid. So hydrochloric acid, strong acid, it's going to have a negligible, its conjugate base, Cl minus, is going to be negligible. I need to spit that out. Okay? So that has no effect because that's neutral. So this brings up the concepts that we've done in a previous video here.